There was one other type of application of L'Hopital's rule that I wanted to mention that I didn't talk about in the information in the previous videos, and so I want to sort of take a look at this. This is the form. This is the indeterminate form. If you have 0 times infinity. Now, what does that mean? Well, we have e to the negative x. Now, we know that as x goes to infinity, e to the negative x, that would give me e goes to the this direct substitution would give you this goes to 0. Right? This is the function e to the x. This is the function e to the negative x. As x goes to infinity, e to the negative x goes to 0. And as x goes to infinity, the square root of x goes to infinity. So this is the form 0 times infinity. Now, L'Hopital's rule only applies when the expression in question, or the expression at issue, is a rational expression, and the numerator denominator needs to either both go to 0 or both go to one of the infinities. And so this does not match that form. The solution is, if it's not a fraction, you turn it into a fraction. Very often, the choice of how to make that occur is kind of obvious. In this particular case, it's kind of clear how we can make this a fraction because this is e raised to a negative exponent. In many cases, it's rather a bit more subtle than that. But in this particular case, so what we have here is this is e going to the e to the x, and so we can rewrite this as limit x goes to infinity. We can rewrite this as e to the x, and I'm going to, since I know I'm going to do a derivative here, I'm going to change this to exponential form on the fly. Radicals don't play well with derivatives. And so now we do have a fraction form, and now as x goes to infinity, the numerator goes to infinity, and the denominator goes to infinity. So this is the indeterminate form, infinity divided by infinity. And so if you obtain the form 0 times one or the other of the infinities, either positive or negative infinity, if you encounter that form, change this into a fraction. Now, it's not always going to be this easy. Suppose we had, it would have to be a different problem. Sometimes it might have to be where you have e to the x, you might need to incorporate an e to the negative x in order to make it become a fraction. In this particular case, it was straightforward. Sometimes that becomes the creative part of the problem, is knowing how to take this expression and change it into one that's fraction form. Once it's in this form, it's straightforward. We can apply L'Hopital's rule. Remember that when you apply L'Hopital's rule, the very next thing you write is LIM. And if this LIM is not present, then this is wrong. What I'm going to write here, what comes up here in the blue, is this blue? What comes up here in the blue is going to be incorrect. This is 1/2 x to the negative 1/2, green I guess this is, over e to the x. So I took the derivative, This is not true. This is a false statement because this limit does not equal that expression. L'Hopital's rule says the limit of this thing is equal to the limit of this thing. And so let's make it correct now this time. As soon as anytime you apply L'Hopital's rule, the very next thing you write needs to be LIM. And the derivative of x to the 1/2 is 1/2 x to the negative 1/2. The derivative of e to the x is e to the x. And now we can rewrite that. I'm going to take this 1/2 and move it out front. Constant multipliers multiply along. And then I'm going to rewrite this as 1 over e to the x times x to the 1/2. And now this makes this pretty straightforward. This is 1/2. In our infinity arithmetic, we're now going to employ infinity arithmetic. So this equals doesn't mean what these other equals means. This equals means equal using our infinity arithmetic notation. As x goes to infinity, this is 1 over. E raised to the infinity power is infinity. x to the 1/2 raised to the infinity, infinity raised to the infinity power, 1/2 power. Let's try that again. Infinity raised to the 1/2 power. Infinity raised to the 1/2 power is still infinity. And so this is 1/2 times 1 over infinity. In our infinity arithmetic, that value is 0. 1/2 times 0 is 0. So that part should be relatively straightforward. This is our infinity arithmetic. And we're going to look at a few more infinity arithmetic problems here in just a bit. But the key is, if you have 0 times infinity, change this to a fraction, and then in this particular case, we have infinity divided by infinity. If you move this piece to the denominator, see, an alternate form would be this. An alternate form would be, we know this given problem is x goes to infinity. We know this is e to the negative x times x to the 1/2. That's the given problem. We could have, and this would be certainly allowed, we could have written this as the limit as x goes to infinity of. We could leave this as e to the negative x in the numerator and then move this to the denominator. This would be x raised to the negative 1/2 power. And now, this is 0 divided by 0. This is now L'Hopital's rule. You can apply L'Hopital's rule here. The particulars would be different. All these negative signs would get canceled out, but you would get the same final result. This will still work out to be 0. That would be a good exercise for you to see if you can work through this the rest of the way and ensure you still get the same final result. This is not probably what you would pitch first, because you're volunteering for extra negative signs. I think the most natural thing to do in this case is to take the negative exponent, move this expression to the denominator, make it a positive exponent, and then I think it's a pretty straightforward computation using L'Hopital's rule.